Hi everybody, welcome back. In the last video we talked about how to solve problems involving conservation of momentum to find either an unknown velocity or, in principle at least, an unknown mass. In this video we will extend that into talking about impulse and its relationship to momentum. So an impulse on an object is defined to be the amount of force acting on the object times the time over which the force is acting. So that's what it is in physics. And I mean, in real life, you often think of like, oh, a certain person is impulsive, like they're very quick to change their mood or very quick to make a decision without necessarily thinking about it. I'm sure we can think of politicians on both sides of the political aisle who are definitely very impulsive. Now, in physics, there is kind of that interesting relationship, which we're going to get to soon. But in any case, an impulse is defined as the force times the time over which the force acts. For a given force, the longer the time, the larger the impulse. Or for a given time, the larger the force, the larger the impulse. And as we'll soon see, we have actually calculated impulses before. So let's take a look at a couple of quick examples. Calculate the impulse exerted on a 5-kilogram object if a force of 6 newtons acts for 2 seconds, or if a force of 12 newtons acts for 4 seconds. So in the first situation, just showing all of our work, we write all of our givens with proper units, and then we show the equation for impulse, check, plug in our givens with the numbers, check, with units, check, and then you have the final answer with proper units. Notice that the units are Newton seconds. Now, we've already mentioned these funny Newton second units before, because remember, a Newton is a kilogram times a meter per square second, so a meter per square second times a second, that's a meter per second. Well, a kilogram times a meter per second is a momentum unit. Interesting. We'll get back to that very soon. For part B, just doing it without showing where the checks would be if this was a question of the day or a quiz or a test. We have our givens, we have the equation, and then you plug in the givens with units and get your answer with proper units as always. Now, what about this momentum stuff? Well, this is the original version of Newton's second law. You might recall that we mentioned it before, that for things happening at least at a relatively continuous rate, but not in some sort of curvy force versus time type of graph or anything like that, the force is equal to the change in momentum divided by the change in time. More precisely, if things are happening in some sort of curvy calculus type way, then we would say that the average force is equal to the change in momentum over the change in time. Or in the way that Isaac Newton originally wrote it, F equals dp dt, where that dp dt denotes a time derivative of momentum. For us, we just care about force being delta p over delta p, change in momentum over change in time. Now, we previously stated Newton's second law, at least we examined it in more detail, as F equals ma. Where we said, okay, well, P equals mv. If the mass is constant, you can factor out the m, and then delta v over delta t, well, that's acceleration. So you had F equals ma. But the original version, F equals dp dt, or delta p over delta t, that's actually true even if the mass isn't constant. And in fact, it's also true if you're going at a high percentage of the speed of light and have to deal with special relativity. This version is always true, in other words. Now, we can take it and rearrange it. Multiplying both sides by delta t, we get delta p equals F times delta t. And that is the impulse momentum theorem. I mean, not incredibly advanced here, but I guess somewhere along the way, centuries ago, people decided to give it a name. Or maybe more likely, decades ago, physics teachers decided to give it a name to make it sound really fancy. So, in any case, the left side, oh, force times time? Oh, that's impulse. That's what we just talked about. So apparently impulse is change in momentum. That's why we call this the impulse momentum theorem. Impulse is change in momentum. So for a collision, the right side is fixed. Remember Newton's third law? In other words, the force felt on one object is equal and opposite to the force felt on the other object, giving the force. But the impulse itself depends on the time of the collision. So if that's fixed, then if there's a small time, that would mean a large force. If there's a large time, this force must be smaller for a given change in momentum. For the famous physics teacher jumping off of a desk experiment, as in the first situation, if the teacher ends up locking the knees upon falling, you hear a big boom, and that's a large force over a small time. On the other hand, in the second situation, if the physics teacher intentionally bends the knees to cushion the impact, that's a smaller force over a larger time. But in both cases, the change in momentum is the same, because in both cases, the teacher had the feet hitting the ground at the same speed, because the teacher was jumping from the same height. So a conservation of energy calculation will tell you the speed. That speed is the same regardless. But in the situation of bending the knees, that speed is brought from whatever it was down to zero much more gradually, because it's a smaller force. That's good, because smaller forces do less damage to joints, whereas larger forces do more damage because it's forces that cause things to break. So again, those units of impulse, well, Newton seconds, but also kilogram meters per second. Use whichever is most convenient for the given problem. Let's take a look at some examples. So first off, in the previous examples where we had calculated the object's impulse, well, let's calculate the object's final velocity if the initial velocity was negative 2 meters per second. So remember, this was a 5 kilogram object. Notice the mass did not go into the calculations before, but we might need it now. Let's find out. So in situation A, we got an impulse of 12 Newton seconds, and we've converted those units to kilogram meters per second. Well, not really converted, but rewritten. So, well, the final momentum of anything is equal to the initial momentum plus change in momentum. We're trying to find the final velocity, but we need to use our momentum situation because we're given the impulse. And impulse comes into this from the impulse momentum theorem, or in this case, just from an obvious P final equals P initial plus delta P. That's true by definition. We're using the impulse momentum theorem in that we calculated an impulse of 12 kilogram meters per second, and we recognize that as the change in momentum. That's using the impulse momentum theorem, equating impulse with change in momentum. So I divided both sides of my equation by m because I want to get my v final by itself. So I plug in my initial velocity, which was given, plus we got this j over m here, because dividing both sides by m doesn't result in it completely canceling. So we do need the mass this time. So we plug it in. Notice the kilograms cancel. That's nice. And we get a final speed of 0.4 meters per second. Now in the other situation, the part B, where our impulse was 48 kilogram meters per second, or 48 Newton seconds, we set it up the same way, and we just plug in a different number for j. And then we end up getting a final velocity of 7.6 meters per second. Yeah, that's a bit faster. Okay, so the impulse momentum theorem, it's also useful in designing bumpers and passenger restraints and collisions. For example, cars are intentionally manufactured to have a crumple zone in the front and rear because that's where collisions most often occur. And in the olden days, cars were not constructed to have this, so that during a collision, the car would often be relatively okay. But the problem is the passengers might not be, because the passengers would end up undergoing a very sudden change in velocity, which means a sudden change in momentum on their bodies, which means small time. That means there was a larger force. But if you have a crumple zone on the car, that means that during a collision, the velocity changes and therefore the momentum changes over a longer time period, meaning that the force is smaller and the people are likely to come out less injured, if injured at all. So that's the purpose of crumple zones. It's using the impulse momentum theorem. So forces can be reduced if the time interval is increased. And if you want it the other way, like you're trying to break a board, then you want a small time interval, so you want to be coming in with your fist or hand at the maximum possible speed, so that delta t is smallest given a certain change in momentum on your hand, which would end up going into the board by Newton's third law. Here's another example. A 65 kilogram runner is moving toward the right at 6 meters per second, and then suddenly sees a squirrel cross the path. This has happened to me many times when running. And then slows down to 4 meters per second to avoid stepping on the squirrel. So if this change in speed took 0.25 seconds, calculate the force exerted on the runner. Okay, Well, let's find out. We write our givens, check. Notice that we also have some signs here that might be relevant because we're talking about going toward the right, so make sure to include those. Or we could just say right is positive and ignore signs from in the future. So we write our equation. Start off with the impulse momentum theorem, or you could just start off with it in the Newton's second law version, F equals delta P over delta T. Either one is fine, and that would get the check if this was a quiz. Well, what is delta P? Change in momentum. Well, change in anything is final minus initial. Well, delta P is m delta V, because P is mv. If the mass is constant, that means that delta P is m delta V. So that's where this next check comes in. You either plug in an mv for each of your momenta, or you immediately realize that delta P is m times quantity V final minus V initial. So I would say that this check would go for either the expression where it is, or the expression to the right. And then we plug in our givens. Notice that we have a minus sign there from V final minus V initial, so we have a 4 minus 6. And then we get our answer, but we need to interpret it. The question is, what was the force? Well, force is a vector. That means the direction is important. If everything was going off toward the right, which was stated in the problem, that means the direction is important, if they stated a direction in the problem. So the force, therefore, would be expressed, your answer would be expressed as 520, check, newtons, check, toward the left, check. The negative sign telling us that it's to the left, because since everything was to the right initially, and we called that positive, positive's to the right. Okay, finally, one more example. A 90-kilogram football player is moving toward the right at 5 meters per second, colliding with a 95-kilogram football player moving toward the left at 6 meters per second. If the 95-kilogram football player bounces off at 2 meters per second toward the right, calculate the final velocity of the 90-kilogram player and the force felt by the 90-kilogram player if the time of contact during the collision was 0.08 seconds. So let's see how that would work. Well, first of all, I'm just going to say that the right direction, the direction toward the right, is positive. So I write down my givens. Notice I have my givens. I also include a proper sign on something going to the left. And then I'm going to solve this using conservation of momentum. So a check for using conservation of momentum and a check for writing out each of the momentum terms. There are two players. I'm going to call them player 1, player 2, as indicated in my givens with their respective masses. So you get a check for writing out sum of P is equal to P1 plus P2 for each of those sum of P's with appropriate subscripts. Now, every P is an MV. So P1 initial, therefore, would be M1 V1 initial. P2 final is M2 V2 final, etc. So a check for plugging in the proper MVs with appropriate subscripts for each of your P's. And then I solved for my unknown variable. I'm trying to find the final velocity of player 1, the 90-kilogram player. So that's absorbed in here. So I need to subtract M2 V2 final from both sides. So I did that. And after doing that, I divided by M1 to solve for the final velocity of player 1. In fact, if I wanted to be cute, I could carry out this and say V1 final equals V1 initial plus M2 over M1 V2 initial minus M2 over M1 V2 final. But I found no need to do that. So we can now plug in our givens. By the way, that check was for either solving for the unknown variable as we did before. The check on the last slide was either solving for the unknown variable here or plugging in the givens first and then solving for it later. You could get the check either way, but I think it's much better form and better practice to do it this way. So now you plug in your numbers with units, a check for plugging in the numbers, a check for them having units, and then you get the final velocity of negative check 3.44 check meters per second. Now, here, since I said that at the beginning of the problem that right is positive, I don't need to state that it's going to the left in my final answer because I effectively already stated that. Because if right is positive, that means left is negative, so the negative sign automatically tells us that it's to the left because I stated it directly. Okay. But they wanted to know the force as well. That was part B. So the force that player 1 feels. Well, The force the player 1 feels is equal to the change in momentum that he experiences divided by the time interval of the collision. So, well, change in momentum is final momentum minus initial momentum. Each of those p's is an mv. In fact, could have just kind of skipped to this step right here with that check immediately, and then plugged in numbers. That's another check, and them having units is another check. Then working out the calculation, you get negative 9,500 newtons. In fact, since we denoted that right is positive, it would be fine to leave the answer like this, but we'll write it out in English anyway, so that would be 9,500 check, newtons check toward the left check. So that is how you can use the impulse momentum theorem combined with conservation of momentum to solve for an unknown force involved in a collision. Next time, we'll talk about how to deal with impulses where the force is not constant, and that's going to be finding the area under the force versus time graph. So we'll explore that then. Hope to see you then, and thank you for watching.